In 1969, NASA engineers faced a highly specific geometry problem. They had to size the footpads for the Lunar Surveyor spacecraft before knowing if the moon was made of solid rock or deep, loose dust. The bearing strength of the lunar surface, the amount of weight it could support before yielding, was entirely unknown. The engineers had to design a physical object to interact with a material they had never tested, seen, or touched. Designing a structural foundation when the ground beneath it is a total mystery remains one of the hardest engineering problems you can face. But you don't have to land a probe on the moon to encounter this issue. Every heavy object that stands on a floor inside a home, office, or factory faces a smaller version of that exact same problem. When you place a piece of industrial machinery in a room, it doesn't actually rest on the floor. It rests entirely on the tiny total area of its feet. All of that mass funnels down into a few square centimeters of contact space. What dents a wooden worktop, marks a timber floor, or lets a heavy cabinet sink deeply into a carpet isn't the overall weight of the object. It's the concentrated pressure at those specific points. This creates a constant tension in industrial design. You choose the foot, but somebody else, often years earlier, in a completely different trade, chose the floor. To understand how extreme this variable can be, we can look back at JPL's post-landing research. When Surveyor 3 eventually returned a 1.3-gram soil sample, scientists tested its bearing capacity. This chart shows the relationship between lunar soil density and bearing capacity. At a bulk density of 1.15 grams per cubic centimeter, the capacity was negligible, but when they compressed that density slightly to 1.9, the bearing capacity shot up 1,000 times. That is a swing of 1,000 times in structural resistance, all driven by a physical property of the soil that you cannot see just by looking at the surface. Designing a product to stand on an unknown surface means trying to solve for hidden extremes that are completely invisible to the naked eye. Back on Earth, human regulations actively try to tame this unknown variable. Guidelines like the ADA accessibility standards and OSHA walking surface codes dictate the exact physical conditions required for public floors. If you read these codes carefully, they don't treat the floor as a neutral, empty plane. They treat it as an active, load-bearing component with strict physical duties attached, demanding that it explicitly resists movement and deformation under applied force. To enforce this, institutions use empirical standards like ASTM D2240. This is a standardized test that measures exactly how far a metal indenter sinks into a material to put a numerical value on its hardness. We rely on these empirical tests because a predictable, universal formula for hardness simply does not exist across all the different floors, carpets, and panels manufactured today. So the person drawing the foot of a machine has to make real physical trade-offs. You can draw larger feet to spread the load and protect softer surfaces, but they consume usable footprint and can make the product look clumsy and unrefined. You can use softer feet that are kinder to the floor, but then the machine might creep and drift across the room under its own vibration. You could add leveling feet to solve the problem of uneven ground, but that introduces extra cost, added height, and a new mechanical component that can eventually fail. This leads to the ultimate economic compromise. If you size a foot to survive the absolute worst possible floor it might ever encounter, you are over-engineering and overcharging for every good floor it ever meets. All of these constraints have to be balanced incredibly early in a product's life cycle, long before manufacturing ever begins. The contact area, the load paths, and the way the base structure spreads the weight of the machine must be locked in during the initial concept phase. These aren't superficial trim choices you can swap out right before shipping. Contact points are foundational geometry, and that carries a permanent consequence. Every designed object will eventually hand off a portion of its load path to a surface it does not own and cannot inspect. The true, often unglamorous discipline of product design is engineering a safe foundation for a surface you will never get to specify. Design decisions are cheap when they are just a sketch, but they become brutal once the physical tooling begins. It requires complete foresight from the very first line you draw. Built for design teams. Depix. Design Intelligence.